Hello, this is chapter 2. It's about transmission lines. And this is our first lecture. We estimate about 10 lectures for the topic. The first lecture will get us into why study transmission line as related to the circuit size and the frequency of operation. We'll get after that into transmission line analysis. We'll develop the theory for transmission line analysis. The circuit theory will be used to develop that analysis. Later on, in actually the second course of the sequence 3106, we'll be using the field theory instead of the circuit theory. In the circuit theory, we are going to look at the physical model of the transmission line, the wires themselves, how much resistance, inductance, capacitance, and conductance this has, and we'll be using tools that are familiar to you, like Ohm's law and Kirchhoff's laws, to develop the analysis itself, and we'll be seeing that later this lecture. The analysis will be done using the transmission line as a distributed physical model, because those RL and CNG are not lumped at any particular location on the line. They're actually uniformly distributed throughout. We'll be doing the development for the steady-state harmonic excitation, and we'll be doing that both in the time domain and the frequency domain, and you will be seeing that as we go on. First, we get to the first point is why study a transmission line, and actually before we say that, what is a transmission line? A transmission line is used to refer to those wires that connect devices to each other, the interconnect wires. Okay, now we start by discussing what is a transmission line. And the pictures here that we have show some samples of transmission lines that are kind of familiar. You've seen around working in the laboratory or even around the home and the equipment that we use. I'm sure that you've seen the twisted pair wire. If you peel many of the telephone wires or the power lines and electrical cords, you will see this kind of a arrangement here. Basically, two wires that are twisted on each other, and there is a jacket that keeps the arrangement protected and intact together. This can also be in the form of multiple twisted pairs, and that's a typically used cable. The jacket is here, and there are about 8 wires here, 4 pairs of 4 transmission lines. Each one of them is again a twisted pair, and a typical connector that goes with this kind of arrangement is the Ethernet connector that you may be using in connecting your desktop or your network modem or hub or what have you. This is the RJ45. It's a plastic thing that keeps the wires in certain order to connect to devices. Here's another form of transmission line. These are the what you may call the parallel conductor or the parallel wire arrangement. 2 wires that are spaced from each other by an insulator, and there's a shielding jacket around here, and the protective jacket. The shielding jacket is another conductor that shields these 2 wires from the outside world, and a similar one is here, except it doesn't have the shielding. These are basically the 2 wires. This is another arrangement of parallel wires, except you have multiple of those. This one here is not supposed to be twisted that much, otherwise its characteristic would change a little. Obviously, depending on the frequency of operation. We'll get to that in a minute. Here's another arrangement here where you have what we call a coaxial. Now this is cylindrical conductor, and there's another outside cylindrical conductor in the form of the shield, and a jacket that covers all that. That is typically the kind of transmission line that goes into television equipment. So this is familiar, or the famous F connector in the TV industry. Same arrangement of this coaxial is right here in these three transmission lines, but the connector is different. This is the known to be the RCA connector, is used in the audio-video connectivity. Video is usually the yellow, and the audio right and left channels and the other colors. This is a BNC connector connected again to a coaxial cable or coaxial transmission line. The BNC connector is a push and twist kind of connector that I'm sure you've seen it in the laboratory, connecting to the oscilloscope and other devices, signal analyzers and network analyzers and stuff like that. All these are sort of what we may refer to as control geometry transmission lines. And the point is, if you go in the cross section of the arrangement here, it should be the same everywhere. In other words, the cross section is controlled, the spacing is controlled, the material isolating them is controlled, so it's controlled everywhere. So the length of the wire is kind of uniform. Same thing here, you know, same cross section everywhere, same cross section everywhere. Obviously there is some disturbance around the connector area. It's not the same exact configuration that you had before. That's always the case, right? But the transmission line itself, the cable itself, is control geometry. One would say, how is this control geometry? Well, if this was put straight, it would be control geometry. If you twist it that far, obviously the geometry here can be altered depending on the degree of twist. Same thing here, the twisting of these wires. If it is uniform twisting, you know, you may claim some control geometry, but obviously there is the amount of control here, or the amount of uniformity here, is not as you see it here, and certainly not as much as you see it here. These kind of transmission arrangements here, or connecting wires arrangement, is not controlled by any means. You can see here that depending how you connect, you know, depending how you twist those wires, you may get different configuration. So why do we study transmission lines? What's this about size and frequency that we kind of mentioned at the beginning of the lecture? Well, if you were to look at a circuit operating at a given frequency, that frequency corresponds to a certain wavelength, all right? As we know, the wavelength would be the distance in space, or in the media where this wave exists, between 2 points of a similar phase. In this case here, we're showing the 2 points are the top or the peak of this sinusoid. That distance here between these two peaks is the wavelength. Okay, that in that particular medium, on that particular space, corresponds to a sinusoid or a cosinusoid that experience a 360 degrees of phase change. That 360 corresponds to that distance of travel. In this diagram here, we just simply expanded that. Okay, so here's a 360 degrees, all right, that corresponds to that wavelength. So if we have a piece of wire that is a piece of wire of this particular length. This is distance, so that's the length of the wire. This particular wire here corresponds to a phase change, all right, of about 50 degrees. Suppose we have that, and that piece of wire is connecting between this node and this node, physically spaced by that spacing or that distance. So voltage wise or current, whatever that signal reflects, correspond to a change in phase in that voltage by that much, and therefore we can never claim that these two nodes have the same voltage. You can see now that the levels of this node and that node are different, and therefore that wire is connecting between two different voltages, and there is a gradual change in voltage along that wire. As you can see, it's no longer the same simple picture that we used to have as a wire connecting two nodes results in the same node. And that simply is why, or that's particularly the case in which we have to consider transmission line theory. Well, let's take the other example here where that piece of wire here is much shorter than the wavelength. Where is the wavelength? It's actually twice as this distance here. This is actually lambda over 2 because we are going from peak to valley, all right? That's lambda over 2. That's only 180 degrees. So if this piece of wire corresponds to a 10 degree of a phase change here is not much. Well, if we take it around here, the 10 degrees here may be a bit more because the sinusoid and cosinusoid have different sensitivities. But anyway, you can tell that the error in this case is much less than the error in that case. And simply because the frequency here is lower, the wavelength is larger, and the size of the circuit or the size of the wire is much smaller. So to conclude, the size of the wire or the size of the transmission line compared to the wavelength, it's that ratio, L over lambda. The smaller L over lambda, the smaller would be the error that we have to worry about. That means at low frequencies where lambda is large, which was most of what we've done in the past, DC or 60 hertz or even 1 megahertz or these kind of frequencies, the size of the wire here could very well be much smaller than the wavelength, and therefore the error would be too small. And we don't have to worry about going through transmission line theory and using the analysis that we are about to get into. Well, to develop an appreciation to that threshold of circuit size relative to wavelength, let's look at table 2.1. In this table, basically, we have three columns. The first column is, suppose I am willing to accept an error of 10% in my signal analysis, or 1%, or in some other cases 0.1%. For each one of these errors and these percentages here, what would be the circuit size that I'm willing to tolerate? And that's basically the L over lambda. How much L over lambda? Okay, that corresponds to that error. So I take that 10% and convert that to degrees. 10%, I'm using the sine this time because we said that the sine is a bit more sensitive than the cosine. So the arc sine of 0.1, which is 10%, is 0.1. The arc sine of 1% is 0.01, and the arc sine of 0.1 is 0.001. It's almost like a linear function. That particular delta phase error corresponds to about 5.7 degrees. Here is 0.57 degrees. This is 0.057 degrees. And if I were to relate that to the 360 degrees, that means I divide delta phase by 2 pi. That means L over lambda that I can tolerate in this case is like 1.6%. L over lambda here is 1.6 0.16%. Here's 0.016%. So you can see now, depending on how much I'm willing to tolerate, this is the size of the circuit that I can accept and neglect in my analysis without going into the transmission line theory approach. Now, how is that at different frequencies? That's what we do in this particular table here. But this table here is a metric. And since we are familiar more with the English system, so I'm just going to look at this particular part of the table. All right. So let's go down a little bit and look at that. If I'm operating at 1 Hertz, my wavelength is 186,411 miles. That's quite a distance. And if I were to tolerate 10%, that means I can tolerate 0.016. That's 2,971 miles. So any circuit less than that dimension can simply ignore the wire connecting two nodes. Right. Now that's assuming obviously that there's no internal resistance of that wire. In other words, it's the ideal conductor. Obviously if there's a resistance there, that should be taken into account. Now if I go up in frequency, let's go to 1 megahertz. 1 megahertz, the size of the wavelength is about 1,000 feet, right? 984 feet in particular. That means 10% error, I can tolerate circuit sizes up to 15 feet, which is quite a distance still. You know, a wire of 15 feet will give me 10% error. A wire of 1.5 feet will give me 1% error. A wire of 0.15 feet, which is about a couple of inches, all right, will give me 0.1% error. Okay, let's go to 1 gigahertz. 1 gigahertz, you have 11.8 inches for your wavelength. That's almost a foot, right? 12 inches is a foot, right? That means 10% error is 0.18 inches, 0.2 inches. That's, you know, not much. 1% error is right there. 0.1% error is right there. So if we go to 10 gigahertz, the wavelength is about 1 inch, and that means 0.02 inch is gonna give you a 10% error. And obviously, you know, if each 0.02 inch give you 10%, and there are more and more elements to your circuit, that error is going to accumulate and things can be a disaster. If you want to go to obviously 0.1% error, that means about 0.2 milliinches. That's not much. So as you can see, you know, operating at high frequencies, most circuits that we are familiar with would be in serious trouble if we just ignore those interconnects. All these interconnecting wires have to be taken into consideration. It may not hurt to look at those numbers in metric, because you know, you need to develop that appreciation to the metric system, because that's what we use in the MKS system of units. At 10 gigahertz, the wavelength is 30 millimeters at 3 centimeters, right? Which is slightly bigger than an inch, right? 3 centimeters. Now, at 0.1% error, that means you're talking about 5 microns. So a circuit of 5 micron size will give you a 0.1% error. So we now get into the development of the transmission line analysis, and we mentioned that we are going to be focused on controlled geometry transmission lines.